Hello, everyone. Welcome to a new session of the Gamma Seminar. It is a pleasure for me to introduce our speaker today, Professor Manuel de León from the ICMAT and the Spanish Academy of Science, who will talk about graded Poisson Dirac and graded Dirac structure. So Manolo, thanks for accepting our invitation, and the floor is yours.
Thank you, Xavi, and thank you, Javi. In principle, this is a paper that we finished yesterday, but we have yet some few things to fix. But I think that everything is correct, and so I will try to explain how to extend the notions of Poisson structures and Poisson brackets and Dirac structures to the case of classical field theories. And so I will record some known things about mechanics. You have a symplectic manifold M with a symplectic for omega. For any function f, one has this Hamiltonian vector field is f, defined just contracting the symplectic form by the vector field, and this is the differential of f. If you take the Hamiltonian vector field for the Hamiltonian function h, we can consider Darboux coordinates, and then this is the expression of the Hamiltonian vector field. The integral cube satisfies the Hamilton equations, and the evolution of any observable f is given just applying the Hamiltonian vector field to the observable f's. So the derivative of the evolution of the observable along the flow and along the Hamiltonian flow. Okay. In addition, if we have a symplectic structure, we can define an algebraic operation in the algebra functions on the manifold, defining the bracket Poisson. It's just the bracket of f and g is just omega applied to the Hamiltonian, the corresponding Hamiltonian vector fields. This bracket is skew symmetric, satisfies the linear rule and the Jacobi identity. And we obtain, we will call a Poisson manifold. So a Poisson manifold is just a manifold with a bracket in the algebra function satisfying these three properties. This is sometimes call it a locally algebra in the sense of Kirillov. But this algebraic structure on the algebra functions can be interpreted as a geometric tensor, a geometric structure on the manifold. We can define the Poisson tensor as this by vector lambda. Just lambda of df dg is the bracket of f and g, and we extend lambda to any pair of one forms. And the integrability, the Jacobi identity, is now expressed by the vanishing of the Schouten-Lagrange bracket of lambda with itself. So this is important, the system of these Poisson brackets, because we can express the evolution of the observables. Just the evolution of f is just the bracket of f and the Hamiltonian. For instance, the constants of motion, the first integrals, are obtained just taking the bracket of f with the Hamiltonian. This is zero, so the f is a constant of motion. And we can study completely integrable Hamiltonian systems, the Liouville-Arnold theorem, Kant theory, axiom-angular coordinates, and also the Poisson bracket is a key instrument for quantization processes. We need to have a bracket, a Poisson bracket, just to obtain this quantization in the sense of Dirac. Okay, so it's natural to think that, well, how to extend these things to the real or classical field theory, because this is good for mechanics, but it's not so easy how to extend this concept to the case of Hamilton, of classical field theories. One first thing is just to extend the notion of symplectic structure, and this has been independently developed by three independent groups in the 60s, the past of the last past century, and introducing this so-called multisymplectic geometry. But in the last 50 years, there are many people working in this idea how to use this multisymplectic geometry to extend the other things, and even the notion of a multisymplectic geometry was not completely studied, and I think that this paper with Alberto Iborra and Franz Cantrin, we study maybe for the first time the geometry of a multisymplectic manifold. Well, how is the geometry? Not thinking in application, but also just the pure geometry of the multisymplectic manifolds. And in other paper, we extended the brackets. In this paper, also with Franz Cantrin and Alberto Iborra, and the idea in this case was to take instead of Hamiltonian vector fields and one forms, we consider multi-vector fields of any degree and the corresponding higher degree differential form, because the multisymplectic form allows for several levels. And in this talk, I will present some results containing these two recent preprints with Rubén Izquierdo. So let me record some.
Manolo,
Yes.
I hope you don't mind I interrupt you. You know, this seminar is open to comment and everything.
Oh, yes, of course. Of course, no problem.
Yes, let me tell you, maybe you already know, but these works about multisymplectic geometry, many of them, you know that they were done by Polish people, Tulchiev and...
Yes, of course. This is, yes. These three groups are the group of Warsaw, and Gormish and Stenberg. The other group was Pedro Luis Garcia, Per Rendon.
I wanted just to tell you, to recall you that people from Warsaw, they don't believe in it anymore. But maybe you are not surprised by that.
But my point is that they even these groups, they don't study the geometry. They use the form, but they don't study the geometry of these manifolds. Like, for instance, you are interested to study symplectic geometry, the properties of symplectic geometry, submanifolds, and other things. So, and in this paper with Alberto and Franz, we try to study the geometry. So we have before we can classify multisymplectic manifold, these things. How to obtain the root coordinates in this case, and so on.
Yeah, interested. Yeah, thank you. That was a comment.
Yes, thank you. So let me record some well known for many of you, but not, I don't know if for every one. But what is Lagrangian field theory? We consider a fibration pi y over x. And we fix a volume form on X, and we can choose favorite coordinates is mu uy, such that the volume form can be expressed in this way. We consider the dimension of the basis n+1, so this is a matter of choice. And of course, the coordinates on X represent the space-time, so the coordinates are the time and the space. So if we take, we have theories of 1 + 1, 1 + 2, or the contrary, 2 + 1, or okay. So it depends on the one coordinate in the time, and the rest are the coordinates of the space. But this can be many different things. And well, this is just a notation for the calculations. And we consider the first order jet prolongation of this section pi from y to x. And so if we consider the space of one jets of local sections, this is the space that we don't know by zeta. I like the notation introduced by in this book by Binks, Sniatyski, and Fischer, which is very simple. So I prefer to use zeta for J1 pi. And so this is another manifold. We have the different projection. We can introduce coordinates in this manifold zeta. We have the x mu. We have the space-time coordinates. The ui are the coordinates of the fields, and zeta y mu are just the derivatives of the y with respect to the x. So we are the derivatives of the field, because we are considering only first order theories. So this is the scheme for this Lagrangian picture. And so, well, this is another technical thing. This one can use the volume form on E just to define this vertical endomorphism. This is similar to the vertical endomorphism used in the tangent bundle. And using, if we give a Lagrangian form, this script L, we have the volume, so you can express L as L times eta, and this L is a function on zeta. We use these notations, which just the notations for the generalized momenta, this p hat, and this p hat mu I is the momenta corresponding to the zeta mu, and this p hat is the energy. So this is will be the Hamiltonian at the end. And so we can construct this Poincaré-Cartan n plus 1 form, theta L, and the Manuel differential of this form is the Poincaré-Cartan n plus 2 form, which is this form. And so we assume that the Lagrangian is regular. This means that this Hessian matrix is regular. And so, well, this is the case we consider. And there are two ways to obtain the field equations. One is just to consider a Ehresmann connection in the fibrillation zeta over x. And so this H is the horizontal projection, and these are the vertical local vector fields generated the vertical subbundle, and this is the expression of H with some Christoffel symbols gamma y mu and gamma u mu nu. And we can compute this, we can perform this computation, and it is easy to see that if this is 0, so if we have a connection satisfying this equation, then the rest is 0, and you can immediately see that if this Ehresmann connection has an integral section like this, sigma, so one can prove that we obtain the Euler-Lagrange equation for this from this equation. Of course, there is a problem here because the connection is not flat in general. So this happens in classical field theories. Is one of the main differences with mechanics, because we deal with distributions, and the distribution cannot be integrable, or in this case the connection is not flat in general. Okay, another approach is just to consider, instead of Ehresmann connections, and this is the favorite approach by the people from Barcelona now and Tarragona, is to consider the composable multivector field. So this is equivalent to find a multivector field such that the contraction of omega L with this multivector field is 0. And we do the same if we consider an integral setting of this multivector field. So the solution satisfies the Euler-Lagrange equations. Okay.
Manolo.
Yes.
Sorry, the assumption that they are decomposable is used in many works, yeah, not well,
Yes.
in Barcelona, yeah, but many people, when they find technical things, they used to restrict themselves to it. Is like that, or there is some way to avoid it?
Because you consider this appropriate. This is the reason because I prefer for these things to use the approach using Riemann connections. You can see immediately here that these are the multivector field is just this obtained from these local vector fields.
Mhm.
The multivector field, if we call this x mu, the
Mhm.
multivector field is x1 wedge xn
Okay.
plus 1.
Mhm.
And this is the composable
Yeah.
and transversal. The two things are the composable and transversal, but this is the reason.
Okay, thank you.
Okay, so this is just how to obtain the equations. And to develop the Hamiltonian counterpart, instead to have the one jets of local sections, the manifold one jet local section, we consider this. I don't know how to. Okay, I don't know how to. You see the whole screen. Okay, well, anyway.
Yeah, we see it.
Yes,
Yes.
because well, I have this. Anyway, it's okay.
It is right.
It's right. Okay, so we can consider for we have again this is the bundle configuration y over x, and we consider the n+1 forms over y such that these forms vanishing with applied to R vertical tangent vectors vertical with respect to the original configuration figuration y over x. And so, well, the elements of this for R equal to 1, any element, and you can do the computations very quickly. Any element is expressed in this form: P dn+1 x. And also we can consider the n+1 forms two semi-bases. So in this case, any form belonging to this bundle of forms is just expressed locally in this way. And of course, we have canonical projections of this bundle over y and over x. And we consider this. We have a sequence, a sequence of vector bundles: 0, lambda 1, lambda 2, and the quotient. And the quotient is just we don't know by zeta star, and is in some sense is the dual affine bundle of zeta. And so we have coordinates. These coordinates are just this is mu uy, p, and p mu y. And we can prove that this manifolds, any bundle of forms has a canonical, a tautological form. If we consider a bundle of n+1 forms, this theta is a tautological n+1 form defined as follows. At a point omega, applied to x0 is n, is just omega, which is an n+1 form, applied to the projections on the base on y. And this is the multimomentum Liouville form, just the natural extension of the Liouville form in the cotangent bundle. Because for n equal to 0, lambda 1 I is just the cotangent bundle. And we consider the minus differential of this canonical Liouville form. We obtain the canonical multisymplectic n+1 form. In this bundle, the definition is the same for any bundle of forms. You can do the same definition for even if we skip these two, so we will take the total n+1 forms, and we can do the same definition, and all these forms are the restriction of the canonical form defined on lambda n+1. Okay, so we can consider a Hamiltonian form. Hamiltonian form in this case is a septium because there is a projection of this bundle of forms into zeta star, because zeta star is the quotient. In local coordinates is given in this way, I will denote by minus h this p, and because this is a septum, and so p is a function of these coordinates, and this is fixed, and this h is the Hamiltonian function. We can pull back the canonical form here to zeta star, and we do the same things again. We consider a connection in the sense of Eisenman of this bundle zeta star over x, and we do the same computation, and we can prove that a connection satisfies this equation if and only if the integral local sections are the solutions of the Hamilton equations. This is just the expression. So this is and of course we can do the same using multivector fields, and instead of this equation we have the contraction of omega with a multivector field x is 0. Okay, and of course we have the Legendre transformation for from zeta to this bundle, which is at the in essence is just the canonical momentum, the canonical Liouville form. This is the local expression, so we can recognize here the energy, and this is just the momenta. We can project this Legendre map using this projection from to the lambda n plus 1 into zeta star, and we obtain the true Legendre transformation, and we can prove that the Lagrangian irregular if and only b, this is a local diffeomorphism, and we can connect both sides of the picture, Lagrangian and Hamiltonian, and the connection are related, everything. So it's just like in mechanics. I will skip this thing because it's not it's the same thing. So this is the how to use these forms, and people call it multisymplectic forms, just to obtain the field equations in the Lagrange side and the Hamiltonian side, and how to connect both sides. But we are calling multisymplectic this n plus 2 form. But what is a multisymplectic form? So in this paper that I referred with Ivor and Catherine, we study multisymplectic vector space like you study symplectic vector space. So this is a multisymplectic vector space. It's just a vector space with a k plus 1 form, nothing else. And we have this mapping from vectors into forms just contracting by b, so we obtain a k form. And sometimes people say that this is when this is injected, we call the form multisymplectic, but we consider this is a regularity condition, but it is not necessary to use this regularity condition for most of the things. So this is the case in classical field theories, but we don't need to put this condition. So
Manolo,
sí,
is
yes.
a pair of comments and a pair of questions. The first thing is that these conditions sometimes I saw in the literature that is called one injective or one regular, and this multisymplectic or pre-multisymplectic, they are called sometimes even plectic forms or things like that.
Yes, there are. Yeah, you're right. There are many different names for these things.
Yeah, the interesting thing is what you said, that for what follows, you don't need such a thing.
Yes,
you can
this is
work
the
pretty
point.
much. And I have a question. But I have a question, because there are lots of definitions. Have you seen any work with, for example, the so-called two injective symplectic forms? I mean, you know, the contraction with any vector.
And this is the point, because why don't consider this kind of thing? So, but the point is that you don't need to. If you have this condition, you can refine some results, but but you don't need to use this regulatory condition just to obtain the result, because the point is that you want to have brackets, and as we can see, we will see that we don't have a bracket, we have a graded bracket.
Okay.
And so this is the point.
Okay, yes,
so
that clarifies what follows.
Yeah, and so, well, this is, in principle, we will denote by this BQ, well, consider a Q multivector, and the contraction, we obtain a K plus 1 minus Q, minus Q.
Okay, yeah, I see. Okay, great, thank you.
Yes, this is the way we will use. Of course, we have the notion of multisymplectomorphism. Is that the same notion that in the case of symplectic or symplectic vector spaces, and well, and even we can obtain some result that say if you are in these conditions, then your multisymplectic vector space is multisymplectomorphic to these models. But I will skip this these things here. But the interesting thing is you can reproduce, it's more complex, but we can reproduce the notion of orthogonal complements, like in symplectic vector spaces. But now we have this possibility to have different degrees of complements. So because we have a higher order form, so we have all these possibilities, and we can obtain the algebra of this for these complements. This is the usual thing in symplectic, the symplectic algebra and symplectic vector spaces. And we also can define the same notions that in the symplectic case, a subspace called isotropic, isotropic, Lagrangian, but depending on the degree of the complement. And observe that here we have this, we have to add the kernel of this B1. If you consider multiplicative force such that the B1 is injective, so this is 0, and we have the same notion that in a previous paper with Mantrin and Igor. And of course, one can consider this kind of models of spaces. I will skip this thing because it's not, we don't have time to go to the, but this is just when you study, for instance, in Abraham Martin, symplectic vector spaces, the first condition is that you have a vector space L, and the direct sum with L star, with the dual, you obtain a symplectic vector space. And any symplectic vector space is symplectomorphic to this model. We have more or less the same in the case of multisymplectic forms. I will skip this because I'm too technical. And of course, we have the notion of the symplectic manifold, and we will consider only a manifold equipped with a closure K plus 1 form, nothing else. And of course, we have the same definitions pointwise of complements and so on. And this is just the model of multisymplectic manifold. Just we have a manifold L, the space of the bundle of forms on L, and we can define, and this is just the same definition that we did in the Hamiltonian pictures. And of course, this is the local expression. There's nothing interesting. We can even to consider these particular cases when we have a regular distribution on the manifold L, and we have these other models. And of course, we can prove that under some assumptions, one multisymplectic manifold is multisymplectomorphic to one of these models. So this is and so and in this case, we can obtain Darboux coordinates, because if you have a multisymplectic manifold which is multisymplectomorphic to one of these models, you have the Darboux coordinates, like in the case of a symplectic manifold, which is locally equivalent to a cotangent bundle, and so this provides the Darboux coordinates. Okay, so in general, if we have a multisymplectic manifold of order K, we can consider a multivector field, and this contraction, giving a multivector field of order of degree K, we obtain a K minus a K plus 1 minus Q form, but we assume that we have a multivector field, which is called Hamiltonian multivector, when this is the differential of a form, alpha. And the form is called Hamiltonian form. So in this case, we don't have this isomorphism between vector fields and one forms. So not all the multivector fields will provide a Hamiltonian form. And so we can consider the space of Hamiltonian multivector fields of order Q, this is this thing, and the space of L forms, this is notation. Okay, so, and this permits to obtain brackets. How? How to obtain brackets? If you have a Hamiltonian multivector, U, this can be the alpha or the beta. So this means the alpha minus beta is closing. So we have a mapping from multivector fields of order Q into this quotient, because this is the quotient of forms by closed forms. And this is well defined. So this is just the projection. We have the mapping onto this space, and we project to the quotient. And okay, and also we would like a mapping, an injective mapping. So so to have that, we only need to quotient the multivector fields of order Q by the kernel of this BQ, and so we have isomorphy between these spaces. So these are not multivector fields and forms. There are classes of multivectors and classes of forms. But this is well defined. And so we can consider the sum of these spaces. And so we will end up with this graded algebra with a graded bracket. Okay. And we can do that simply because here we only need to consider the Skeuton-Annius bracket. You have two Hamiltonian multivector fields U and B of degrees P and Q. So this bracket is a Hamiltonian multivector field of degree P plus Q minus 1. So this can be proved immediately from the definition. And so using this equality, and we can prove it's a very simple proof. We have this well-defined bracket here. These are classes. You have these classes. This class, a representative U. This class, a representative B. We obtain the Skeuton-Annius of U and B and the class. So this is well-defined. And we have another bracket on the other side on classes of forms. It's not defined in this way. This is well defined and satisfy all the properties that we want. This is skew symmetry, but of course taking into account the grades of the forms, and this is the Jacobi identity. And to have a graded algebra, we need to change, because we need something like that. And so to have these things, we need to change the definition of degree. So the degree of this alpha hat is not the degree of alpha, is K minus 1 minus the order of alpha. This is a technical thing. But with this technical thing, we immediately obtain that the degree of the bracket of alpha, of the classes of alpha and the class of beta, is just the sum of the degrees. So, and this is okay. And so we can define this new bracket define it on classes of forms in this way, using this signature in front of the bracket. And so everything works, and so this is a great linear algebra. And so we have the similar thing that we have in symplectic geometry. We have the Hamiltonian, the bracket, the Lie bracket in this case of Hamiltonian vector fields on vector fields, and we have the corresponding bracket in the Poisson bracket on the space of forms. And the difference is that now we have to deal with classes of multivector fields, classes of forms, and this graded Lie algebra. So one can see that the correct approach to multisymplectic or to classical field theories is just to use graded things. Okay, this is a technical thing that we don't need to. Okay, so I will skip this and also this, because now this is just to deal with currents and so on. This is the equivalent to conserved quantities in mechanics, but it's not necessary to. Okay, so let me go to here. So with the intention to extend notions in Hamiltonian mechanics to classical field theories, there are several approaches tries to define the same notions. And so one of the things that, well, this is my personal opinion, that people that know about Poisson geometry don't know very well classical field theories, and on the contrary, people interested in classical field theories don't know many things about Poisson geometry. So there are 3 attempts to develop higher order notions. One of the points is that people started to extend not Poisson brackets, not Poisson bivectors, but Dirac structure. What is a Dirac structure? A Dirac structure is just a construction as follows. We have a manifold, and we consider the Witten sum of the tangent and the cotangent bundle, and a Dirac structure is just a vector subbundle of E satisfying some properties. We have this bracket, which is just the evaluation of one forms over covectors on vectors. And in addition, we have this another bracket, which is also the Courant bracket, which is defined in this strange way. This is the Lie derivatives. And this is just introduced independently by Ted Courant and by Irene Dorman. And many people work with this Dirac structure, because Dirac structure is a way to take at the same time presymplectic structures and Poisson structure, because if you have a presymplectic structure, we have a mapping from vectors to covectors of vector fields to one forms. And so we can consider the pairs. Is alpha, with alpha is the contraction of omega with the vector field x. And if you have a Poisson structure, we have a mapping from covectors to vectors. And so if we consider in both cases the graph of these mappings, we obtain as vector subbundle of these things. So this is a way to consider at the same time both things. And so a Dirac structure is just a subbundle satisfying some properties of integrability. For instance, is Lagrangian with respect to this pairing, the natural pairing, and is symbolic with respect to the Courant bracket. So this is the definition. And in the presymplectic and symplectic fit in this notion, this definition, and the same thing for Poisson structures. So this is a
Manolo,
Yes.
Yes, a comment. Kogan and Dorfman made define the brackets a little bit different, yeah, because the
Yes,
Koran is
yes,
antisymmetric.
yes.
It's not. It does
Yes,
not hold the Jacobi identity, and the
yes,
Dorfman
yes.
is the other way around. Yeah,
Yes, you are right. I would like to stress the role of Dorman, because Dorman passed away in an accident, and so she cannot continue working in these things and many other things. So, but there's a different approaches. In some sense, Dorman is more algebraic than the Curran. Yeah, but that is true. You can go to the Irene Dorman has apart from the papers, has a wonderful book, and she.
It's interesting because there are equivalent approaches. At the very end, on L, both they give a Lie algebra, yeah, both
Yes,
structures.
yes.
But at in calculations, Manolo, I don't know about you, but for me, the Dorfman was easier to make calculations. But
Yes,
I don't know
I
if it's
think
my
so.
feeling or something.
Yes, and so the pity is that the work of Dorman is not so well known as the results by Curran. For instance, the Curran bracket. So, but this is probably because he died, and so people don't know don't knew about her. So this is but the notion are the same. At the end, are the same steps and small things. So this is the problem with people try to extend Dirac structures. And so in this paper with by Joris Vankesever, Hiroki Yoshimura, and Melvin Leko, is in 2011, they define a multi-Dirac structure. A multi-Dirac structure is, okay, we have a manifold M. We consider for any P, we consider this Whitney sum of the multivector fields of order P and the K minus 1 minus P forms, okay? And a multi-Dirac structure of degree K is just a sequence of vector subboundaries D1, D2, Dk. The P is a vector subboundary of this EP and satisfying some properties similar to the Dirac structures. For K equal to 1, so we have the usual Dirac structures. And so,
sorry, Manolo. One curiosity I wanted to ask: is there any multi-Poisson? Because you said that Dirac is a generalization of Poisson.
I will go just to this.
Okay, great.
Yes, but this is interesting to know about the evolution of these notions along the time.
Okay, I see that
Along
you wrote it
the
indeed.
first 14, 15 years, there are several attempts to define these things. And I will I will talk at the end our own approach, just to put some order.
Great, because it's very interesting. I found this multi-Poisson of things like that, but
Yes,
I don't
yes.
know what to do with them. Indeed.
Yeah, but yes. So we will propose another thing just to avoid these different names and so. But this
Great.
is the first attempt. Just this Vankesever and collaborators approach, because they are very interested into define the analogous, because one of these papers will be a paper with Jerry Martin, and Jerry Martin passed it away, and so this paper does not exist. But the idea was just how to extend this notion of Pontryagin bundle, because Martin to the Whitney sum of Tn and T star n, he called it Pontryagin bundle. We don't use these names. We use the Skinner and Rax formalisms, because the Skinner and Rax develop a formalist for mechanics in this context of Tn plus T star n. But anyway, this was just the idea of Vankesever and collaborators, just to have an extension of this Pontiac mount to higher order. Okay, so we did some things, and this is another approach by Marco van Boom in 2012. And Marco noticed that giving a multi-Dirac structure in this sense, then D1 determines the rest. So you have D1, you have the rest. And he introduces a new notion. He called it higher Dirac structures of order K as a Bendorster bundle satisfying a list of properties. That's the usual properties. And Marco Zamon proved the equivalence under some assumptions of multi-Dirac structures and higher Dirac structures. So we have two names, multi-Dirac structures and higher Dirac structures. So we see the complication. And Enrique Bustin gave another notion. In this paper, a brief introduction to Dirac manifolds proposes a definition of higher Poisson structures generalizing the usual ones. And the idea is very simple, because if you have a Poisson structure, we have a mapping from covectors into vectors, from one forms into vector fields. Well, you can change one forms by k forms. And so he considered a subbundle, a vector subbundle of the space of k forms, and a mapping from this space of k forms to Tn, satisfying some properties. And this is the bracket. So this is the bracket defined, and with this property or this sharp mapping. And so we have another different definition. For k equal to 1, so these are the notion of classical Poisson structure, and this is just the morphism due by the bivector, by the Poisson bivector. And this condition is, which is, you can see, oh, sorry. Oops. Can be strange, so it's nothing.
By the way, Manolo, the brackets, could you show again the brackets? Yeah.
Yes.
It's a la Dorfman. Yeah.
Yes.
Rather.
Yes.
Yeah.
Yes, because
Okay.
Enrique is not, he don't work in symplectic mechanics. He works in Poisson geometry.
Okay.
So I think that this is just the things that are behind all this history. But in any case, well, this is just the same thing. And in another paper with Nicolás Martínez Alba and Roberto Rubio in 2019, observed that the graph, because at the end we need to consider the graph just to have a Dirac structure. The graph does not define a higher Dirac structure in the previous sense, and so they weakens the conditions and introduce the weak higher Dirac structure, and they call this higher Dirac, just to have a notion compatible with the rest of the things. So, and this is the graphic. I thank to Ruben to do this beautiful graph, and you can see all these things. So graded Poisson, higher Poisson, graded Dirac, multi-Dirac, higher Dirac, with higher Dirac. So this is a confusion. So what is what? Okay, and so this is our proposal. How to put some order in all these definitions and to introduce more clear definitions. This means the following. We know to extend the notion of symplectic form, symplectic structure. We have multisymplectic structure. Okay, this is new. But we had to extend the notion of Poisson structure. In this case, we don't need to use higher Poisson or any other word. This will be a graded Poisson structure because we don't have a tensor, a Poisson tensor of order greater than 2 we have by vectors, but in the different grades. And the same happens with the bracket. We don't have a multi-bracket, or no, we have brackets of two things, classes of forms, but graded. And so this is the difference. So I think that we can, this is our intention, we will put some order. And our proposal is that the people use these definitions instead of the previous definition, because you can see that you need a dictionary just to know what is the structure that we are using. And of course, in the way to develop graded Poisson structures, you need to use these graded Poisson structures to define the corresponding graded Poisson brackets. And if we have graded Poisson brackets, how to obtain a graded Poisson structure. And at the end, to define graded Dirac structures just in the right way, including multisymplectic or pre-multisymplectic, multisymplectic in our sense, and graded Poisson structures. And so we will have not a multi-Dirac, but we will have a graded Dirac structure. So this is the point. And so how to do that? Well, we started to study the things first in the linear case, and then in the case of manifolds, to study definition to manifolds. And this is just the same notation used by Van Kersaver and the other people, which is the pairing. And so we define a graded Dirac structure in this way. So a circle of subspaces, we are in the linear case, D1, dk, dp is a subspace of EP, for satisfying these properties. And again, we have this is just a notion that extends the previous notion when it has a weaker property. This is not the most interesting thing. Okay, so we have a mapping from linear graded structure to linear with high-grade Dirac structures, and we will prove that this is indeed a bijection, so they are the same things. But to prove this, we need to give equivalent notions of graded Dirac structures, equivalent descriptions. So this is a technical thing, and we can prove that indeed linear graded Dirac structures of the K are equivalent to this corresponding one-to-one. Okay, and also we consider the case from manifolds, and this is just to extend the things to manifolds, so point-wise. And we define first an almost graded Dirac structure because we don't impose the condition of integrability at now as a family of vector subbundles from a manifold, and so satisfying the properties the point-wise that in the other case. For the integrability, we use this graded Courant bracket, and so the condition is that this should be involutive with respect to the Courant bracket. So this is there is this operation take sections here of the grade P and the grade Q, and obtain something which is in the grade P plus Q minus 1. Okay. And so we have this equivalent between graded structure and high Dirac structures. So this is the definition. And again, we have this injection. I will skip this thing because it's very technical, and I prefer to go to the final thing. Well, these are just the definitions. We obtain the definition of graded Poisson structures, more or less in the same, but not exactly the same thing. It's more general. Our definitions are more general than the previous definitions. So you can see that it's more or less the case of boosting, but we don't impose these conditions about with this this x01, so this is not zero in general. Okay, so this is a gradient Poisson structure. So we have this family for any A, satisfying these properties. So it's very technical, but it is just the thing that we need. And so this is indeed a graded Dirac structure. So we are working things in the right way. And okay, this is another relation between the Poisson structure and Hagler Poisson structure, because are trying to relate our notions with the notions regularly defined by all these three groups of researchers. And another interesting thing is that when you have a Poisson structure, you have a symplectic foliation. So we have the same thing when you have this graded Poisson structure. We can obtain a multisymplectic foliation. So this is just this theorem. If you have a graded Poisson structure on a manifold, then M may admit a multisymplectic foliation. So the leaves are foliated by multisymplectic forms, like in the case of symplectic geometry. So we also have the notion of graded Poisson brackets. So we need to, if you have a graded Poisson structure, we can repeat more or less the same thing, the same procedure that I described for multisymplectic forms, and so we can obtain the bracket, satisfying all the properties that we need. And the converse, if we have a bracket satisfying these properties, is there a graded Poisson structure defining these brackets? Yes, this is the result with some. It's not. There are some technical things that we need to solve just to obtain the result. But well, it's one can do the thing, and so we have the bracket. So okay. Well, these are technical things, and so we obtain exactly the same thing. I will go to here. Well, this is just the case of the multisymplectic form in any level. But this is again a technical things, and we have the corresponding answer to graded Dirac structures. It's just a graded definition of, so we can, well, this is very technical, but this is just the idea. So excuse me if I pass quickly of these things, because this is just I will go to this figure, because you can see the case in mechanics. You have Dirac structures, and inside presymplectic and Poisson structure, and you have an intersection, because some presymplectic, for instance, symplectic manifolds are also Poisson. And so using these notions, you obtain the same thing in the case of graded things. You have graded Dirac, graded Poisson, and multisymplectic forms. We have a technical thing, because the forms, these mappings BP cannot have a constant rank in principle. But not this is
Manolo,
yes.
one question. In classical mechanics, you will have also Jacobi a little bit with and without Dirac structures, and you will have some
Well, this is our
multi-Jacobi, yeah, or something
this
like
is
that.
our plan.
Ah.
This is our plan
Okay.
for the next months, just to stand all these things to
Okay.
to the case of multi-contact.
Okay, great. It will be
And to
okay.
obtain
That's
the same things. In this case, the good thing is that we don't have a multi things for multi-contact.
no, great. Yeah,
structures.
yeah.
So we can go
Cool.
directly to the right definitions. But you can see that this if we compare this graphic. No, sorry. Oh, I don't see I passed too fast and okay. Yes. This is very complicated thing. So I think it's more easy to have this more simple graphic just to and the correspondence is just wonderful. So the only thing is that all these results are very technical and the proofs are very long and very technical. But at the end, the point is that you cannot. For instance, what is the importance, for instance, of Dirac, graded Dirac structure in classical field theory? Because you have a classical field theory, we have all these things. So the point is that if you have a graded Dirac structure, you have multivectors of some degree and the corresponding forms.
Mm-hmm.
If you stand only in for vector fields, you will have vector fields and currents.
Mm-hmm.
But the idea is have to have intermediate things, and this is important in physics. There are many people working in this intermediate situation. Currents not of the higher, the possible higher.
Mm-hmm.
And so you can recover these things using these graded things. So in classical field theory, things are graded. It's the natural. But if you put multi, you can understand that you have, for instance, you put multi-Dirac, but you can understand that you have not a vector fields or not pairs. For instance, you can confuse with Nambu or other or these things. So, but we have things we have pairs, we have bivectors, we have the brackets of two things, not of anything. So this is the idea. In multisymplectic geometry, the things are graded. So it's the natural thing to think
And as you said, there is well, considerably lot of people working on this thing, yeah, and the applications in field theory.
Well, this is a part of a preprint that probably we will put in a shift in a few days.
It would be nice to have it if you can send out.
Not yet.
I mean, when you will have it.
Yes, and so I think that people use these notations instead of the previous notation because it's very complicated to well, I had to, and in our paper, all the things are related. So every of these concepts has the equivalent or the generalization of the corresponding notion in the other approaches, in other approaches. So my intention is that people use these things and not the others. Just in order to put some easy notation.
That is interesting, of course. Okay, thank you.
I read that I cannot provide all the details because the proofs are really are
Time consuming, yeah. It's
yes.
field theory. Proofs used to be long and complicated, yeah. It was the
Yes.
usual stuff.
Yes.
But you know, if you
But the
have
notions are
sound
clear.
ideas, yeah, and ideas are clear.
Yes.
What you want.
Hmm.
But proving it is absolutely a different story. That's you know, Manolo. Sometimes I make jokes about people saying, "No, the idea is clear. The proof has to be easy." Yeah, it's
No, the proof
we
is
do
not
this in
easy.
mechanics, and yeah, that's the point.
The proof you can ask Ruben if the proofs are easy or not.
I mean, I have experience. The thing is that I have even been a referee for papers saying, "Well, we have done this for mechanics, for field theory is exactly the same." The same idea, so it goes straightforwardly. I used a couple of times. I asked some guy to prove it. Some little
Yes.
things that you can imagine that the the review took a lot. So
Yeah.
well, you know what I mean.
In the paper, we recovered some recent results by Juan Carlos Marrero and Francois Gaibalmat on brackets. They use the affine approach just to different brackets, and we use part of the research just to study. The last setting of the paper is just devoted to study currents and conserved quantities.
Okay. Well, Manolo, do you have anything? Because I don't know if you reached the end or
Yes, I
that
think it's
you.
just in the end because so this
Mhm.
the next.
Yeah, I didn't know. Okay, so thank you, Manolo, for your nice talk. Thank you. A large, interesting, a really huge talk. I mean, you have talked a lot of things about very general things. So, is there any question, remark, comment?
Maybe as a possible remark is that, as I said, like there are a lot of definitions and you can get lost quite easily because there are a lot of similar names and one just have the weak adjective next, then you have almost, but as Manuel said, there is like the simple idea of just having the Dirac structures and Poisson structures on a graded basis. Because you may have not only conserved quantities of the highest order, but also why not conserve quantities of A forms, which are closed on solutions, right? So we wanted to extend this, but on a graded basis. And these are technical issues, but maybe the things that we introduced are not technically exactly the same, but on the important examples, which are under some regularity conditions, they are. These introduce like more, these are richer with more structure, so it should be easier to work with these definitions than the previous one. So I just wanted to say like this.
Any other question?
Only I think we started to, because our idea was to study probably some of you heard the talk by Ruben in El Escorial. And so it was the idea just to study the brackets, but we discovered all these papers, or Mankel-Schaber and all the people, and so well, we try to understand what these people say, and so this is the reason to finally write this paper.
By the way, Manolo, this is huge. I mean, you can do lots of things with this, don't you?
Well,
I mean,
I think that the Ruben is very good. And the first thing is that I asked Ruben, well, and it is written in my blackboard in my office in Madrid, and so how these three definitions put on the blackboard, and then what these things are doing. So so this is the way just to understand all these things, just to, because it's not you are lost in this
zoo of structures. Yeah, yeah. Lots of things. But
Yes.
the thing is that there are lots of definitions with several differences, but main results are very similar in many many things of them. So I have a wild question. Maybe I don't know if it's a bold question, stupid question, whatever, because you are dealing with very lots of theories with differences, with different relations between them, with a zoo, yeah. But you have a common structure, more or less, of theorems on properties that, of course, they are difficult to prove. They are very technical at times, but they look the same. When one sees things like that, one think about category theory, because you start thinking about theories from the sea of a bird, from very far away from them, and you see that you have many different things, different with technicalities and things like that. But at the very end, the corpus, the main core of all the theories is the same. So have you ever think of someone ever think about doing some categorical approach to it?
I always remember this. The was by Michel Talleyrand was the last Albert Prize. And Michel Talleyrand says that, well, to understand a theory, you need to go very, very high, just to look the thing from a very high level. And
this is Grothendieck's idea.
You understand the things. If you go to the particular cases, you don't understand nothing. So you need a
very wide approach.
Yes.
Okay. Thank you. So, any other question? No. So let us thank the speaker again. Thank you, Manolo, for the talk. Thank you very much, and see you in a week. Yeah.
Yeah, I was about to say that next week we're having Eduardo García Toraño from Argentina, who will talk about route reduction and these kinds of things.
You are all very welcome. We hope to see you again, and see you now in a week.
See you.
Thank you, Manolo. Take care.
Bye.